video on related rates of change. This is one of the I guess main applications of calculus that we kind of look at, differentiation, and the key understanding that we need in order to do these questions is going to be the use of the chain rule. Okay, so I'll just write the chain rule down up here. The chain rule tells us that dy dx is dy du by du dx. So that's really all that we need to sort of get into this. Basically what we're going to do is we're going to get two different derivatives, and then we're just going to multiply them to get some other rate of change. So got a couple of examples here. We're also going to have a look at a VCAR exam from methods from a few years back, and we'll just see how they go from there. So first one, water is being poured into a cylindrical tank with its circular base on the ground at a rate of 2 meters cubed per second. The tank has a radius of 2 meters. Find the rate of change of the depth of water in the tank. So I think one of the first things you need to do in a question like this is firstly check that your units are at least all the same. We've got volume being measured in meters cubed, time is being measured in seconds, we've got the radius being measured in meters, so it looks like we're all okay here. Okay, what I'm going to do is I'm going to draw a quick diagram. So we've got a cylinder with the circular base on the ground, a radius of 2 meters, and it's got some water in it filling up to a certain point. Okay, and we'll call that the depth of the water. I might even just call that, H for height of water, just to make life a bit easier. Now, we're also told that water is being poured in at 2 meters cubed per second. So what that tells us is that the rate of change of volume with respect to time is 2 meters cubed per second. Now, given that the radius is 2 meters, I can actually write an equation for the volume. And that would be volume equals pi r squared h, but in this case r is 2. And so the volume is equal to 4 pi h. Now, if I know that the volume is 4 pi h, then that means I can get dv dh, which is actually just going to be 4 pi. And I could put the units on here. I mean, it's volume with respect to height, so that's going to be meters cubed per meter. The last thing is to use our chain rule. We're looking for the rate of change of the depth with respect to time. So we want rate of change of the height with respect to time, and by using the chain rule I can say that that's dh dv multiplied by dv dt. So just applying the situation that we're sort of dealing with here. dh dv I get just by flipping this one here over, so I can say that dh dv is 1 on 4 pi. And so we have 1 on 4 pi multiplied by 2, which we could simplify that to just be 1 over 2 pi. And that's going to be measured in meters per second, because it's height with respect to time. Anyway, that's the first example. Second one, given x equals sine t minus cos t and y equals half sine 2t, find dy dx. So this is a really nice application of parametric equations. Okay, so we have the x component, we have the y component, both in terms of t. Well, that's all right. So I'm just going to differentiate each of these separately. I'm going to get dx dt. So sine becomes cos, cos becomes negative sine, and I'm going to get dy dt here. 2 will move out the front, so So it'll cancel out with the half and just be left with cos 2t. So then I can say that dy dx must equal dy dt by dt dx. Again, just using chain rule. And, well, dt dx is just going to be dx dt, but, well, flipped over. So that's going to be cos 2t multiplied by 1 over cos t plus sin t. So that just equals cos 2t over cos t plus sin t. And I think that should simplify because we've got cos 2t, which we can use our double angle formula. So that's going to be cos squared t minus sin squared t over cos t plus sin t. And the numerator factorizes using difference of two squares. So cos t plus sin t, and then cos t takes sin t over cos t plus sin t. And so they can cancel each other out. Like so. Whoops. Well, there we go. And so in the end we are just left with cos t minus sin t. So there we have it. The last thing I want to do is have a look at the exam question from methods from several years back now. It was a bit of a classic question. I'm just going to make room for it down here. So let's swing over and have a look. Here we have the Tasmania Jones question. Now, Tasmania Jones was a very famous person in the math methods exams for about 20 years, and Tasmania Jones actually sort of retired in 2015, so sorely missed. But here's the question. So we have a Zambezi tribe with a precious marble and tied to a rope, suspended 6 meters above the top of a vat. The vat is an inverted right circular cone with a radius of 4 meters and height of 8 meters. Well, that's interesting. So there it is all there. Blah, 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 blah. At the same time, acid begins, of course, to be poured into the vat at a constant rate of 9.4 meters cubed per hour. Well, that's a rate of change of volume with respect to time. So I might just actually, we'll keep track of that one for later. Okay. And the statue is going to dissolve if the acid touches it. Right, we're not going to work through the whole question, but I really just want to show you the related rates part of this question. So firstly, show that H equals 2R. Well, you can perhaps see there that we have two similar triangles. We have the small triangle in the bottom, which is made of the acid, has a radius of R and a height of H. We have the larger triangle from the cone, which has a height of 8 and a radius of 4. So, to do this first part, I know that the radius compared to the 4 must equal the height compared to the 8, okay? Just using ratios here. So R on 4 equals H on 8. And I think we need to show that H equals 2R, so multiply by 8 on both sides to get the answer. So that's not too bad to begin with. Hence, find an expression for the volume of acid in the vat at time t in terms of H. Okay. So, part B. The volume of a cone is 1/3 pi r squared h. But we want it to be in terms of h. So I'm going to turn this here around to make it so it says r equals h on 2. And then I'll substitute that into the equation here. So V equals 1/3 pi times h on 2 squared multiplied by h. And simplifying that, I'm going to get V equals pi h cubed on 12. Okay, that's the second part of the question. So we've got volume in terms of h. Show that dH dt is increasing at 9 on h squared meters per hour. Rightio. So let me just check that again. So we want dH dt. Now looking at this, I should be able to get dV dt, dV dH. So let's just write that one down to begin with. dV dH is going to be pi h squared on 4. And we were given information in the question at the beginning that I said we'd hold on to. We're going to use that now. We've got the acid being poured in at 9 pi on 4 meters cubed per hour. So that means that dV dt is 9 pi on 4 meters cubed per hour. Right. So we're all good to go now. We can figure out dH dt using the chain rule. And so there's going to be dH dV by dV dt. And to get dH dV, I just need to flip this one here over. So that's going to be 4 on pi h squared multiplied by 9 pi on 4. The pi's cancel out, the 4's cancel out, and we're left with 9 on h squared as we need to show. Anyway, that's really all there is to it, so I'll leave the video there and we'll see you in the next one.